I'm Stephen Tovey. I'm in the developer tech group at AMD, and I'm going to talk to you today about memory management. So hopefully no nodding off, especially you guys at the back.
That's not the name of our group, Steve. We're not the dev tech group, we're the game engineering group.
Whatever. that's my job title, so I assumed I was in that group, but hey ho. So this is the agenda today. So I'm going to go through heaps and types, different sort of constructs in Vulkan's memory management sort of stuff, few tips and tricks, and I'm going to talk a little bit about VMA, which is our open source memory allocation management library thing. So let's get started here. So just to sort of motivate the talk, this is why we're talking about this. This was all of our lives, I guess, not so long ago. We had a minimum level of control, but it didn't really require much effort to use the APIs. And these days, we've sort of traversed this huge arrow, and we're sort of around here where we have a lot more control over how things are going. We can do more interesting things, but it takes a lot more effort to get there. So yeah, this is Vulkan and also D3D12, but this talk's just going to focus on Vulkan. So it's interesting here, we've got a good balance of control and effort, and we can do interesting stuff like optimize the memory footprint of our games down. We can target more specific platforms. We have the sort of the levers we need to pull to do that. And we can do interesting things like aliasing, so we can keep our memory footprint down again. So this is a sort of motivation for why I'm stood here talking to you. So let's get started with heaps and types. If you've done any Vulkan coding, this flow will be probably quite familiar to you. You will start by creating a resource or describing the resource you're going to create. You'll create that resource, and then you've got to figure out from that what sort of type of memory you want, the alignment of it, and the size that you need. You've then got to allocate that memory, and then you sort of bind the two things together. So you end up down here with the description of your resource and the memory that backs it. You bind the two things together, so you have this sort of notion of the resource and the memory that backs it. So this is the flow that we're interested in. And we're mostly going to focus here on this guy, on this side, allocate memory. So to allocate memory, unsurprisingly, you call VK allocate memory, nicely named API, and it takes a pointer to VK memory allocate info, which describes the allocation. It's pretty much obvious. I mean, this is all boilerplate gubbins that goes in every struct, mostly in Vulkan. The allocation size, yeah, that's not so complicated. But this guy down here, memory type index, that one is a little bit weird. If it's not immediately obvious just from looking at the struct, what is that thing? Why is it important? How do I select what type index I choose for my allocation? So the way you choose it is by using this stuff. So at the start of your game, most likely, or your app, you will query the memory properties of the device, and you will get back a structure called VK physical device memory properties. Inside there, you've got a bunch of types, a bunch of memory types, and also a bunch of heaps. The index that we referred to on the previous slide is an index corresponding to the memory type. Types and heaps have a sort of connection to one another. So a memory type corresponds to exactly one heap, but a heap can contain multiple memory types. So on this slide, this is for an RX Vega 64. We have, and this is on PC Windows. Everything I'm talking about mostly is PC Windows. We have 3 heaps here. 2 of them are in this column on the left, which is the graphics memory VRAM column. So 2 of the heaps are in VRAM, and we've got 1 heap here, which is in host memory or system RAM. And they sort of match on to the corresponding memory types. So heap 0 exactly matches to type 0. Heap 1 has 2 types, which you can sort of use to allocate within that heap. And heap 2 also has just a single type down the bottom here. So onto the sort of main meat of this section here is this chap. So I sort of put this table together with a hope that you would maybe print this out and look at it, or like refer to however you're going to refer to documentation. But I tried to put together something that would give you a quick reference guide about what types you want and what properties those types of memory have, and then hopefully you'll be able to think, well, I'm going to look at, I need to allocate something with these properties, what type do I want from this column down the side. So just to walk you through this table a little bit, down the left-hand side here, this column, memory type, is the type indices. And just to be 100% clear, this is for an AMD RX Vega 64. If you put a green graphics card in, you will have a different table. If you put a blue graphics card, well, if you're using an embedded blue thing, you will have a different table. But this is for AMD Vega 64. It's mostly the same on other AMD products. So anyway, down the left-hand side, we've got the memory type, so that's 0 through 3. So they correspond to the types we had on the previous slide that were all connected up to the heaps. And then we've got these 3 columns, the next 3. So we've got storage, visible, and cached. And they are properties of the graphics card. So a tick in that column, that first column, means this thing lives in graphics memory. A tick in the next column underneath the I means this is visible to the graphics card. And a tick in the third column where the cache is means this is cached by the graphics card. We have the same concept for these 3 columns. Need to be very careful with rows and columns, I'm realizing with this. In these 3 columns, so we have, it's in host memory, it's host visible, and it's host cached. And then the next 2 columns are the operations that you would do on that memory, so read or write. And the icons here are lifted from Aesop's fables, I believe. So a hare means it's quick, and a tortoise means it's slow. Obviously, in the fable, the tortoise wins, but ignore that. For our purposes, we mean hare is fast, tortoise slow, okay? No deeper philosophical meaning to these than that. And then on the far right here, we have the CPU's speeds for operations, so read and also write from the CPU side. And we have the same sort of iconic notion here to sort of communicate the speeds of those things. And down here is just some random notes. So that means that this guy corresponds roughly to VK memory property device local bit in the memory property flags, which is a property of your heap. So if you've got a memory type that has a tick here, it means that the heap it came from has that bit set in it. These 2 over here roughly correspond to these 2 bits here, so host visible and cached. So a tick in those columns, a tick in those columns there means that these bits are set on the memory type. Hopefully everyone isn't completely head explode at this point. Right then, so let's have a walk through these and see if we can deduce some useful information from this table. So type 0, so we're going to go across this top row here. We know that there's a tick here, so that means it's in video memory, so it's in VRAM. If we use this memory type, our allocation will be in VRAM. It's visible and cached by the GPU, so the GPU can see the memory. That's quite unsurprising. It's in VRAM, that's good. It lives in the cache hierarchies of the chip, so it's going to go in the L2, the L1, etc., all the various caches on our GPUs. And because it's got a tick in the VRAM storage column, it must therefore have a cross in the host memory, because the memory isn't going to be in 2 places at once. So that's why that's got a cross. And if you noticed actually down the table, everywhere you've got a tick for graphics storage, you will have a corresponding cross for host storage. So logically consistent. And in this case for type 0, we can't see this memory from the CPU, so you can't map it. It's only visible by the GPU. And it's not cached, obviously, because it's not visible. And therefore, you can't do any operations on it, so we have big crosses over here. And the read and write speed is fast. So in this row here, this is more or less what you think of typically when you think of VRAM. This is your sort of bread and butter as a graphics programmer. You put in your render targets in here, you put in your static textures in here, you're putting your static vertex data in here. Anything that sort of doesn't change, this is a good shot for this. And if you don't need CPU access, obviously. Okay, so type 1. We can see it's not in GPU memory, it's in CPU. And it's sort of visible and cached by the GPU, as all of them, so I'm going to stop saying that now. And it's also visible by the CPU, but not cached. So because accesses are going over the PCIe bus, we know that they're not going to be as nippy as stuff in VRAM. So we've got a couple of tortoises, what's the plural? Steve will know, what's the plural of tortoise? Tortoises, okay, we've got a couple of tortoises down here. And yeah, obviously not as fast. For reading on the CPU, that's going to be a tortoise because it's uncached memory. So it's not going to live in our CPU's cache hierarchy. So every time we read, it's going all the way to memory and bringing it back in. Writes, however, get a hair. And the reason is because of write combining. So if you write nice, linear, sort of streaming type of model to this memory, it's going to be nice and quick. So that's type 1. Type 2, we're now back in GPU memory again. It's obviously visible and cached, so it's not in CPU memory. It's also visible to the CPU this time, so that differs from type 0, but it's still not cached by the CPU. So for this memory type, we have a couple of hairs for the GPU. It can read and write quickly. It's in device local memory, and it's uncached, so it doesn't have to do anything smart to synchronize up with the CPU. But the CPU is still a tortoise for its read. It's slow reading, it's uncached, so it's got to bring it in. It's actually even a bit slower probably than this guy because it's got to go over the bus to VRAM. But write speed, again, is reasonably quick. And again, this comes down to write combining. So if you're going to do this nice streaming model, you're going to get reasonable write speed from the CPU. And finally, type 3 down, type 3 down the bottom. Now we're back over in host memory again. Except we've got ticks all the way along. So we can see it and cache it on the GPU. We can also see it and cache it on the CPU. So what does this mean? It means that every time we touch it from the GPU, it's going to be pretty slow because we're going to have to go over the PCIe bus to the system RAM to read the contents of this. It's also going to be a little bit slower because we're going to have to snoop CPU caches because of that tick there, which means that this memory is cached on the CPU, so we actually snoop caches for that. But read and write speed will be reasonably nippy from the CPU because it's cached, we can do reasonably quick reads, and we can write quickly as well. Again, it's cached. So, a couple of caveats here. These tortoises here, if there was some sort of like genetic hybrid tortoise with the ears or whatever, I would have put this here because you get some caching behavior from the GPU. So on the first read, yes, you're in tortoise mode, but once you've warmed your caches on the GPU, hopefully you're going to start hitting there, and that will then be quick for subsequent accesses of the same data. If you were to stream through this memory, then yeah, okay, you're in this mode. But if you get a decent cache hit rate here, then these become less bad. Also, a quick note about this column. Currently, for PC Windows, I think everything we tested, all the vendors so far, everything that's marked host visible is also marked coherent. So this is why it's sort of glossed over here for Windows development. But on other architectures, so potentially on Linux stacks, on other mobile things that I don't know anything about, these functions may be your friend. So after touching memory with a write on the CPU, you might need to flush your mapped ranges to make sure everything's coherent and synced up. And the same goes for reads that you want to do. So you need to invalidate those ranges before you read them to make sure that you're not reading any stale stuff out of your caches. And just be aware that unmapping buffers will not do this for you. You have to manually do this. So currently for PC Windows developers, this is okay, but things change. So just be aware of these chaps here. Okay, so back to our heap type map that we had to begin with. I've now added these usage notes. Hopefully, as I was going through that, you were thinking about your applications and your games and thinking, well, yes, I would use that type for this and this type for this. But I've added some notes here. So type 0, heap 0, this is our super fast GPU read and write, no CPU access. This is your bread and butter, this is your render targets, this is your depth buffers, this is your static textures, your vertex buffers. This is where you need all that stuff. As we heard in the previous talk, if you end up putting render targets in there, that isn't going to be particularly good for you. So you really want to make sure that all the sort of mission critical stuff is in here, really. Type 1 is more or less designed for staging uploads to VRAM. So you want to effectively stream your resources into type 1 on load, then have them copied to VRAM, and then they just live happily ever after in VRAM for the life of your application or whenever they get destroyed. And type 3 here is effectively the inverse of that. So that's designed for read back from the GPU. So stuff like, say you've got a MIP chain where you're doing some luminance calculations, or you're doing a fancy compute shader to do it all in one pass, or whatever it is, the result that you need on the CPU, maybe it's some physics stuff you're doing in a compute shader, you probably want to put that in type 3 so you can do a reasonably quick read back from the CPU. And type 2 down here is designed specifically for dynamic read once resources. So stuff like if you had a particle system that was updated on the CPU and you were going to write a bunch of instance data or something like that, you might stream the results into a type 2 allocation from the CPU and then read them from the GPU. Warning. Do not encode your memory type indices directly into that API. That is a terrible idea, and you will almost certainly get burned by doing so. The reason is that different vendors have different memory maps. As we said, you call that function to get an idea of the heap and memory type sort of structure of that card and driver. If you hard code indices into that allocate function and then put another vendor's card in, that's almost certainly going to be bad for your health. So please don't do it. The sort of advisable way, I would say, is to try and have some sort of abstracted notion of what these heaps are, potentially based on, the usage, and then have a function that will just map to the sort of indices that you want from there. Okay, so some tips and tricks. We'll start with a little game. So how many people here would make a unique allocation for every structure or class in a C or C++ program? If you're voting for the red box, will you put your hands up for red? One guy with the red, okay?
Yeah, sorry, red for no.
Thumbs up for red if you would do it. Blue box, no, you would not do this. Hands up if you would not do this. Okay, so we had no red and mostly blue. So let's open the boxes. And if you said red, which none of you did, thankfully, you got the shame none, so none of you are getting the 10 hours of bell ringing. And if you said blue, congratulations, you have the happy chappy. You had the right answer. So it's the same on GPU is the good news. So you really don't want to be doing an allocation for every unique resource, every texture, every vertex buffer, every constant buffer. Not a good idea. And it's for similar reasons as you would not do this in a CPU program. You would fragment your memory probably reasonably fast. Performance would be fairly poor. You would have poor data locality, or you'd have minimal control of data locality, and your personal sanity would also probably suffer as a result. So good reasons not to do that. This advice sort of echoes what we heard in the last talk from Ferrell. You probably want to allocate reasonably large chunks of memory and sub-allocate from within that and try to manage that as best you can. Our recommendation is roughly 256 megs, so it's not a million miles away from what the Ferrell guys are doing. They were doing 128. The rationale being, if Windows 7 is a target for you, the allocation overhead is a little bit higher there. So this size for us seemed to be a decent trade-off between flexibility of the size of the chunk versus the overhead of allocating the chunk. So yeah, 256, 128 is probably fine also. Means 16 allocations, you'll fill up 4 gigs of RAM. That's not too bad. And as I said, you just allocate the chunks and sub-allocate within these blocks. So you can use your usual grab bag of tricks from CPU land to manage this memory once you've allocated it. So you could use a linear allocator. You could just have a pointer that you move along every time you put a resource in it. You could do a stack allocator where you have frames and maybe you allocate the render targets here, and then for a level you would put the next set of stuff only for that scene and then free that back, or whatever it is. You could do a double stack where you come in from both sides. If you've got something with fixed size blocks, you could do that with a free list. You could do ring buffers. You could do whatever you want. So any of the tricks that you've probably been using for years on the CPU, you can use all the same grab bag of tricks on the GPU with this. Okay, so another fun question. What happens if you were to run out of device local memory, so you run out of VRAM, and you try to do a VK allocate memory, and you try to request some VRAM? Any votes for the red box? Please put your hand up for red. There's a few hands for red. Any votes for blue? 2 votes for blue.
Pretty sure this is a trick question.
2 votes for blue. Let's open the boxes. Who said red? Well done. You get the happy chappy. If you said blue, you also get the happy chappy. The answer is both are correct, depending on the driver, the vendor, the platform, all of that good stuff that you would put into your test matrix and pull your hair out like I've done. Both are correct. So, for oversubscription, as we've heard from Ferrell on Linux, the allocation fails. The application has the responsibility to handle out-of-memory conditions. And out-of-memory potentially changes per driver, per hardware, if you've got Chrome running, if you've got some other random app running that's allocating VRAM, that might fail at different points. So the application has to sort of robustly handle the out-of-memory conditions. Some drivers on some platforms will return VK success. So what happens is the allocation will succeed, you'll get given some space, but some other pages will get silently paged out of your VRAM into system. You might look at that and say, why would you ever want that? The reason is it is useful for development purposes. There are some good examples of it. If you were prototyping something up and you just, I want to get it working, I don't care. If you've got some artists who are prototyping a scene, maybe they don't need to stick to the budgets, it can be useful. Also, the argument goes that if the system can page your blocks out anyway, due to the user running some other app, then, why not go down this route? It's, no problem. Also, obviously, sort of tied in quite a lot with the first point is that the application doesn't have to explicitly handle the out-of-memory circumstances. The application will still run. Obviously, accessing blocks that have been migrated out of system or out of video memory, that can lead to degraded GPU performance, though, as you might expect. So currently, there's no way exposed to control the residency or to query the residency, so you won't necessarily know that something's got paged out. There's no way to query the used and free currently, which makes this a little bit tricky as well. Also, as we heard, the heaps that we were talking about before, they're going to fill up with your resources, but the driver's also going to create things as well. So swap chains, command buffers, descriptors, PSOs, query results, all of this stuff needs memory, and it all comes out of different heaps depending on the drivers. So it is kind of hard to figure out, where you are in your limits. So we've got a hack for that, which is this. We have some sort of suggested informed adjustments to the sizes of the heaps, which can help you avoid getting paged out. So when you're doing your allocation in your allocators, whatever, if you were to adjust down the heap sizes by the following factors, you may find that you run into less sort of paging issues. This is sort of not science, but it is something that might help. So, yeah. I mean, these numbers you may wish to adjust depending on your application, how your application works, but as reasonable starting points to converge on something, maybe this is a good option. Aliasing. So this is a good way to actually save a bunch of memory. And the idea is that when you are finished with resources, you can reuse the memory for something else. So along this bottom axis here is time. These are different passes from some hypothetical application. So we render our gbuffer, do some lighting, render some alphas, and then do some post-processing. Typically, by the end of the lighting pass, the gbuffers are sat around doing not very much. So there we go, there's no start effect. So why not reuse those resources or use the memory for those resources again later in the frame? And that can save you a bunch of memory. I mean, for a 4K game that's got several gbuffers, that's tens of meg, just sat doing nothing at this point in the frame. So you can use this for more sort of transient resources. You could use it for temporary render targets in a post-processing. Say you were doing some like blurring thing that needed to ping pong back and forth. You could use it as a giant UAV for some compute shader, some temporary memory that you were going to do in your post-processing, whatever. There's 100 million ideas you can sort of use here for reusing this memory, and that's all now possible. So this really is a really good technique to save a whole bunch of memory. One word of caution: if you are going to do this on the second or third use, please make sure that you are sort of stringently assuming that your resources contain garbage. The reason being that at this point, who knows what sort of is in that memory? It could be a gbuffer, but it could be in some like compressed state. I mean, you want to basically throw it away and assume it's rubbish and fill it up with whatever, initialize it to something sane. I had a look for some sort of stuff that was using this, and I think Yuri's actually with us today with his super cool like task graph thingy that he did for Frostbite. I think he was doing automatic analysis of when resources were done with and then reusing that memory, and I think he reported sort of savings up to and over 50%. So yeah, he's nodding, so I'm not talking rubbish. So there are decent wins to be had with this. So yeah, really have a look at this if you're looking to save bytes. Okay, another game. Transfers. Which queue would you use to copy a resource from your host memory to device local? Hands up for the red box, which is any queue with a VKQ transfer bit. Yeah. Hands up for the blue box. I would use the compute queue. One compute queue. Open the boxes.
Not a trick question, Jerry.
You get the dog for the transfer queue bit, and I'm sorry to say you have been shamed with the none. You should probably use a queue with the transfer bit set. So, why? The reason is the transfer queue, at least for AMD, maps to an actual DMA engine that's completely asynchronous from the rest of the chip. So it doesn't touch other queues, and it is actually the fastest way to copy across the PCIe bus. If you can kick your DMAs off early, way before you need them, they'll run completely asynchronously to graphics and compute. It won't need to launch any wavefronts to do that memory access to copy it. If you run something on the compute queue, it's going to actually have to spin up a shader to do that memory access and copy it. So by putting things on the transfer queue, you can sort of offload the other queues. You won't need to clog the GPU up, so to speak, with wavefronts running like blit shaders effectively. And that's more or less what I just said, I think. So for device local to device local, so that's copies from VRAM to VRAM. So say you were implementing a defragger or something like that. This is probably what you're going to do. Then the choice isn't as clear cut. So the peak transfer speeds of doing the shader-based copy, so having a compute shader or something spin up that copies the resources, they'll be faster. However, it will sort of clog up your GPU with these shaders, these wavefronts running this sort of blit shader. So you've got a choice to make here. Do you want to have a faster copy that's inline that's going to stop your shading, or do you want to have a slower copy that could potentially be pipelined against that work? So that's the trade-off you're making. So as we were saying, for a defragger, this is probably the sort of problem you're going to run into. And if you can afford to take the latency hit, then potentially the transfer queue is a good option. You can have things copying in the background, and then maybe a frame or two later, you can update the descriptor and then free the original copy of the resource. The general rules of thumb here are, if you need it right now, so you're you're doing some rendering a depth buffer or something, and you want to copy it away straight away, and you can't afford any latency, then compute and graphics is probably your fastest option. If you can wait, then the transfer queue might be the one for you. Obviously, the transfer queue's got some restrictions, so you need to respect the sort of granularity of the queue. If you're doing a full sub-resource copy, though, that'll be fine. And since we have Mr. Hoodie in the room, I'm channeling Richard here. Measure, measure, measure. You need to make sure that you're making the right choice. So there are costs to using the transfer queue. You've got the semaphores, you've got the synchronization on top. So do measure and make sure you're making the right choice for your specific case. Just a couple of notes on mapping. It's generally okay to have an entire memory block sort of persistently mapped. That's okay. I know on previous sort of APIs, older ones, if you kept something mapped on the CPU and then accessed it on the GPU, that would be sort of suicide. No longer the case, at least on Windows 10. On Windows 7, you might get some issues if you're still doing that at submit or present time. So do take care if you're targeting all the platforms. Also be aware that if you're keeping enormous stuff mapped the whole time, you may impact the usability and stability of your debugging tools. So just a note on that. Resource creation, so another tip here. I've called it lazy mode, but it's not really. It's just stuff you should avoid, stuff that makes your life easier but has a cost. Layout general, that's a sort of obvious one, I hope. You should probably prefer using the optimal versions of these things and transitioning to those. It's more specific for the drivers. They know how that's going to get used in the future, so it can therefore avoid sometimes cache flushes, etc. The more general, marking something as general means that the drivers have to be quite conservative in terms of caches, in terms of synchronization and things like that. So try to be as specific as possible when you're transitioning resources. It will help the drivers. Sharing mode concurrent on render targets depth buffers. This nobbles our compression. So if you switch that on, you won't get compression on your render targets, which can have a bit of an impact on performance. So it's advised that you would use exclusive mode. So you're saying this target's used by this queue, and then manually transition ownership to other queues. And in this way, you'll keep the compression, and then you can manually get the decompress if you need access from another queue. Some other notes here about tally mode. I'm going to skip this, I think, because of time and stuff. But yeah, other bits and pieces you can refer to. Okay, another game. Querying the size of two identical resources. So you've got two resources in memory, two descriptions of resources, so like a buffer or a texture or something, and they've got the same MIP levels. Oh wow, okay. You've got the same MIP count, you've got the same dimensions, etc., and you're going to query the size of them. Will that always give you the same answer?
What driver version? What driver version?
Okay, so you're voting for this one then?
Well, it depends on the driver version.
So you're going to vote yes or no? Red, any hands up for red? For latest Vulkan. Hands up for no? No. A couple of no's, a couple of yeses. Let's open the box. Shame none for the red, unfortunately. And you get the happy dog if you said blue. So yes, memory requirements, e.g. size, they can vary for similar resources. So same things, you'll get potentially different sizes. There are sort of good technical reasons for this and for this flexibility. And just to iterate or just to emphasize, it's not the preserve of spec wonks. So it's a weird corner of the spec. It's like, oh, you know, this could happen in some like moon, like round the sun thing with like a cat dancing on the right hand side. Like maybe this will happen. It does actually happen. So do not cache the results of querying sizes. So if you need to query every resource for its size and use that. Do not cache the results of queries. And it'll save you a lot of headaches. Okay, another tip for allocations to avoid some fragmentation. It's quite tempting to just write some general allocator that can just do anything, and it's nice and easy to use. However, I would advise at least trying to split this up based on size. So having the notion of a small block allocator and then a more general sort of larger block allocator, and then having some threshold whereby when an allocation is requested of a certain size, you can put the smaller ones in one block and then the larger stuff on the other side. And the idea here being that you're going to get less fragmentation if you start freeing small things and sort of chopping and dicing the different blocks of memory. So you'll still potentially fragment both types of memory, but it's more likely to be able to find free spaces in the different pools if you're sort of, statistically distributing that stuff a little bit better. So this is one technique. Again, it's an old trick from the CPU world. I think I did this 10 years ago on a Xbox 360 or something. And yeah, it works. Okay, so just to finish up, I'm going to plug our memory allocator library, if that's okay. Here it is. It's free, it's open source, it has an MIT license, and it's like super hipster because it's like a single header and you can just hash include it and it's amazing and like you don't need to do anything else. It's simple C99 interface and it has the same coding style as Vulkan, so it sort of sits nicely with the rest of your code. You don't have this like weird, ugly other code next to it. It's battle tested. It's used in a few bits of middleware, I think. There's a page on GitHub where it lists all the use of this stuff, so you can see it has actually been used. And it's already getting some love in the community as well. So we've had I think we had a few pull requests, a few contributors. Riss is nodding, so yeah. Towards this, so it is getting some traction. It has functions that help you choose all of the layouts and sizes and alignments. It's got stuff that can allocate blocks of memory, and you can sub-allocate from that. It actually works on sort of 256 meg blocks, or you can sort of configure the block sizes you want to use. It's got a tracker built into it, so it's actually keeping track of where everything is. It respects all of the alignment and buffer granularities and all of that good stuff. It works on every platform that we know of, I think. And that's how it looks. So it's not like, crazy amount of code, VMA create buffer, and it's filling out, it's taking your buffer description, and you give it a more high-level description of the usage, and it will do the allocations in the right memory pools, etc., etc. It actually even has some tooling in the form of a Python script, so you can actually dump the state of the allocator out. It's kind of a similar visualization in many ways to the Feral guys in what they've got in their heads-up display. You can dump the allocator to JSON and generate something like this, so you can immediately see fragmented areas of memory. You can see large allocations here. You can see the different memory types. So this is VRAM, and this is your system memory. You can see the little chunks in here. So yeah, it's useful. Okay, and then just to wrap up, as we all know, Vulkan's lower level than its predecessor, requires more explicit memory management, and creating this stuff is multi-stage. And driver magic that was in the driver is now under your control and is your responsibility. So there's a little bit more to do. You obviously need to deal with the differences between GPUs, but by choosing sort of a sensible abstraction, that's perfectly fine. And it is actually possible, by following decent practice, to make something that works pretty optimally on everybody. And we have this nice library, VMA, which is available now on GitHub. You can go and check it out, and that'll help a lot, hopefully. So thank you very much. Just wanted to thank these guys for their contributions and their reviews for my slides. Yeah, I think I have some time for questions, maybe. Yeah. Wow, okay, hello.
So, referring on the different heaps on the GPU and the CPU, maybe you put the slide with the tortoises and everything.
Yeah, I'll try and get
so,
back there.
Is there, how does it look based on the flags? So, can we infer this diagram
Yes.
exactly as it is from the flag? So, they would look each, what are the bits set on each of these?
Okay, so that guy there maps to this bit.
Yes, so the lack of this one assumes that it's a
System.
It's the second row, right?
Yeah, so if that bit isn't set, it's assuming it's in system memory.
Right.
However, that doesn't tell you anything about residency, it just tells you where you intended to put it.
Yes. So what would be the flags for each of the types? That's basically.
Okay,
so
those two don't have any explicit flags. As you can see, they're just ticked for everything. So just by necessity of it being Vulkan allocations, it's visible to the GPU.
Yes.
Then that column there is the not of that column.
And all of them are host visible.
Yeah, so if it's host visible, then that's this column here. I think I had an annotation for that. There you go, yeah. Host visible is that I, and cached is that.
So type 0 is device local but not host visible.
Device local, not host visible, yes, exactly.
Type 1 is host visible, not device local,
Yeah,
but not host cached.
yeah, no cached bit set, yeah.
Type 2 would be host
Device local
and host visible.
and host visible. And then you've got host visible, not device local, cached. There's a great website, I think it's done by Sasha Williams, where he's running all of this amazing stuff and he's querying all the cards and all the driver revisions for everything and uploading it, and you can just browse every card under the sun and you can basically get this info.
I was mostly trying to figure out that this would be pretty obvious at the time of querying if you knew what you were looking for.
Yes, it should be.
Except of the tricky number 2.
That
This
one.
one would be a bit more tricky to figure out what it is unless you know it like you want. But the rest of them are obvious.
You should be able to infer number 2 as well, I think. It's just device local, host visible without the cached bit.
Yeah.
What happens if you do set
You can't set the bits, so this is the info you get back from the driver, so the driver will tell you this stuff is available. You can't say I want an allocation with the magical combination or whatever. There's another bit as well which is called lazy allocated bit, which I think is a mobile thing. I don't think we use it. But yeah, who knows what that does to this. Yuri, yeah?
I'm very confused about the size query returning different results.
Yeah.
So if that was true, this means that there's hidden state somewhere, and this means an opportunity for a race condition. So you may query size, go away, do some other allocations, go do the actual allocation, and between that time, the size may have changed because the hidden state has changed.
Yeah.
So how can that be? Can you explain?
So the spec just fixed that.
Yeah,
Last
okay.
week's spec update banned drivers from varying size.
Okay, so yeah, maybe it's fixed on the bleeding edge. But previously it was done, yeah, I can tell you offline why it was done, if you like. Hey, Nigel?
Yeah. So I agree we don't make resident, but even on the X, that's so obviously you could page out on contextual, that's fine. But are you saying that you're going to page out even if you're using sparse partially resident images as well?
So your question is if we page out.
Yeah, so if I'm supposed to use sparse partially resident images and using like architecture, you're saying that.
Oh, wow, okay.
So we can talk about this after, but
Yeah.
I'm quite surprised that even in that situation, like the whole point of that is to have line break control of residency. But we'll chat.
Yeah, I can. That's next level. Okay, I'm out of time, unfortunately. So if you have any other questions, please don't wait too long into the beer festival, or you'll get sub-quality answers. But yeah, come and grab me anytime. Thanks, everyone.